Today's lecture is called Light in the Universe. So I want to start off the lecture by just asking people their answer to the question, what is light? So let me know, when you hear the word light, what are you thinking about? What's light? Yeah?
It's a wave in a particle.
Light's a wave in a particle?
Yeah.
All right. Good. So when you think of light, you think, oh, it's a wave in a particle. Anything else? Yeah?
Something I need to see.
Something that you need in order to see. Yeah, okay, good. Right. So, in fact, colloquially, I can't even say the word. That's what we use. That's the word we use, light, when we think about the thing we use to see, right? But is that all light is? More words? What do people say? Give me an answer. I'm going to force someone. Yeah. Sorry? Heat? Yeah, you're right. Light. Heat is also a form of light. So who knew that? Okay, most people. So light is kind of a mysterious thing in the sense that it's hard to describe. It's kind of mixed up, I think, in our minds a little bit when we use the term light, what we're actually talking about. So I decided to ask myself this question, what is light? And so if I had to describe what it was, this is what I came up with. Now, before I go through all these lines, why do I care? Why do we care so much about light? We already have one answer. We kind of need it to see. So those of us who can see like light, because it helps us see. But in the context of this course, where we're talking about the universe at large, trying to understand astronomy and cosmology, why is light so important? Yeah?
It's the foundation of everything.
It's because it's the foundation of everything. All right, I like that. Yeah, kind of. It's sort of like, without light, without studying light, we would really know almost nothing about the universe at large. It's by studying light that's propagating to us from these really distant things that we figure out everything we know, almost everything we know about the universe beyond the solar system. So it's for that reason that I think it's worth some time just thinking about light. And also philosophically, just as a phenomenon, it's kind of a mysterious thing, this light. And so in this lecture, I'm going to talk about not only sort of in the modern world how we think of light and what we know about it, but also historically how humanity came to understand light as it is and the questions that people ask themselves about it. So the way I describe light here is it's electromagnetic radiation. I think that's the most concise way of describing what we mean by light. So it's radiation that comes from electromagnetic activity. And what we generally call light in day-to-day language is the type of electromagnetic radiation that our eyes can detect, that we can see. And specifically, that's light, that's electromagnetic radiation that has a wavelength somewhere between 350 nanometers to 750 nanometers, somewhere in there. That's where your eyes can detect electromagnetic radiation. And that is a tiny, tiny window in the whole electromagnetic spectrum. Light carries energy. Specifically, it carries energy in the form of photons, so the particles that make up light. So the first answer we got is that it's both a particle and a wave, which is true, and that's kind of odd, actually. And the particle that sort of makes up these waves, the electromagnetic waves, we call those photons. And those photons carry energy. Light moves very fast, but it doesn't move infinitely fast. And I think most people are aware of that, because in the modern age, we talk about light all the time and the speed of light and stuff like that. But the fact that light has a finite speed has fundamental implications for lots of things. The distance between the Earth and the Moon, it travels the distance between the Earth and the Moon in 1.28 seconds. So this is a scale picture of the Earth and the Moon. And this is how long it would take a light beam to go to the moon. So that's 384,000 kilometers or so in just over a second. So clearly it's moving very fast. So the speed of light is about 300,000 kilometers in a second. I think I said this in an earlier lecture. Light can travel around the Earth 10 times in a single second. Now, I think most of you know, or at least aware, that electromagnetic radiation, light, comes in all different flavors. And that goes from gamma rays to X-rays, ultraviolet light, the visible light that we see, and then longer wavelength light that we call infrared, TV waves, radio waves, all that stuff, that's all light. So right now, there's all kinds of electromagnetic radiation that's traveling through this room that we can't detect with our eyes. Namely, that's longer wavelength stuff, mostly radio waves. And that's why you're getting internet right now. If you're wireless, you're using a longer wavelength light to do that. So specifically, it's the wavelength that matters. Now, interchangeably, you can either characterize light with its wavelength or with its frequency. And that's because it's really the same thing, because when you take the wavelength and you multiply by the frequency, you get the speed of light. So that's a constant. So you can either use wavelength or frequency. It's completely interchangeable, how you want to describe light. Now, the concept of wavelength is something that probably most of you have seen before, but let me just remind you of what this is. So any kind of wave that you can talk about, you can characterize in some way with a wavelength. And specifically, if you think about the simplest kind of wave, a wave that just repeats itself, like a sine wave or a cosine wave, and you imagine some repetition over space, then the wavelength is the distance between two repeated points on the wave. So the peak of this wave to the peak over here, the distance between these 2 points is the wavelength. So light that has a very long wavelength has a very long distance between peaks, and light that's very short wavelength light has very, very small distances between peaks. And that physical characterization of its size matters. It matters for things. Yeah?
How do you measure the wavelength?
Of light?
Yeah.
You need apparatus. Basically, you need specific instruments that are designed to pick up these kinds of things. And I could talk about that a little bit. So it's understood that light, depending on its wavelength, travels through material differently. So it turns out that light, when it goes through glass, will bend slightly differently depending on its wavelength. And you can measure that bending, for example, and use that to figure out what the wavelength of the light is. That's one way you can go about measuring it. More specifically, you can try to be accurate in determining the wavelength of electromagnetic radiation by understanding how it refracts with how it bends and interferes with itself. So light interferes with itself. All waves show interference, and I'll talk about that later. And by studying that interference phenomena, it turns out that you can back out the wavelength of light as well. But measuring the wavelength of light was something that was kind of a triumph of modern physics, to actually sort of get all that stuff down. And that was something that would have never been thought possible, even several hundred years ago. It would have been very hard to do that. So it's a great question to ask. How do we even know? How do we know this? How do we know what the wavelength of light is? And it's been a bit of a trial to do that. So the one phenomenon that you guys are probably all very familiar with, you've all seen a rainbow and stuff like that, is that when white light, what appears to be white light, say from the sun, passes through a prism, it gets bent out. And it gets bent out depending on what the wavelengths are, such that it spreads the light out into its constituent colors. Okay? So when white light goes through a prism, you'll see it spread out into colors and make a rainbow. Okay, and each color corresponds to a different wavelength of the light that you see. And the reason why this happens is, depending on what the wavelength of the light is, it bends more or less when it passes through the prism. So depending on what its wavelength is, it spreads out more or less, and that's why it breaks those colors up spatially, and you can see the difference. Violet light has a wavelength of about 400 nanometers. And red light has a wavelength of about 650 nanometers. And so red light is longer wavelength light than violet or blue light. So blue light very short wavelength, red light, stretched out, longer wavelength. And by the way, a nanometer is 10 to the minus 9 meters, so this is very small. And it turns out when you're dealing with light, okay, the fact that it is a wave doesn't really show itself very readily unless you're dealing with things spatially that are about the size of the wavelength itself. All right? So light, for example, doesn't really, you couldn't tell that it's made up of a wave if you're doing things like measuring the type of shadow light casts through a door frame or something. Because the door is so large compared to the wavelength of this light that it casts very sharp shadows, and you would never tell the difference between it being a wave and not being a wave. But if you're shining light on something that's small, so spatially small, compared, of order of the wavelength, or 10 wavelengths or something like that, then you can start to tell. It starts acting a little funny. It doesn't act like it's traveling in straight lines. You can see the wavelength type phenomena appear. And that's one reason why it took so long for people to figure this out, that it's got a wave, or convince themselves necessarily that it's got this wave-like nature, because you had to understand, you had to study things on very small scales to sort of know for sure. And I'll talk a bit about that in a few slides. So this is sort of this is a picture of the electromagnetic spectrum. So here, this is what we're most familiar with, this chunk in the middle, the visible light. Okay? This is your rainbow and your characteristic wavelengths. Red over here at long wavelengths, violet over here at short wavelengths. But up here, it's stretched out over sort of the grand scale of electromagnetic radiation that we understand. And you see that what we see with our eyes is just this tiny sliver right here compared to what in principle exists in electromagnetic light. So we're blind to this. Okay, all this kind of light we're completely blind by. Or to, I guess. Right. So infrared radiation is called infrared because it's wavelengths that are longer than red. It's redder than red. And so that's slightly longer than this, about longer than 800 nanometers or so. And shorter wavelength light than violet is ultraviolet. And so the ultraviolet rays are the kind of thing that we worry about with sunburns and stuff like that. And infrared light is what? Someone mentioned it earlier. What's infrared light, colloquially? Or what's one type of infrared radiation? Heat, right, heat. So heat is infrared radiation. When you feel something hot with your hand, you feel that warmth, that's infrared radiation. So you can feel it with your hand, but you can't see it. So in principle, there's all kinds of stuff going on in all of these different wavelengths. AM radio is way over here, very long wavelengths. And gamma rays have very, very short wavelengths. And as I'll talk about in a bit, light that has short wavelengths is made up of very high energy photons. And light that has long wavelength is made up of low energy photons. And so that's the basic reason why you do not want to get bombarded with gamma rays, because those photons are very powerful. You don't want them going through you and messing you up. Whereas these nice, soft, fluffy photons that make up the radio waves, we're not too worried about those, right? So they're going around us all the time, going right through us all the time. It doesn't really mess you up too much, certainly compared to gamma rays. Now, just something that you should know or remind yourself of, that when you're dealing with a wave that's traveling along, and if that wave's traveling at a speed, then there is a direct connection between the wavelength of light and the frequency of the light. So I talked about this before. They're interchangeable. So you can, if you want to tell me what the frequency on your radio dial is to listen to your radio station, you can do that, and I can turn to that frequency. Or if you wanted to, you could tell me the wavelength of the radio waves you were listening to, and I could turn my dial that way too. It's the same thing. Because we're assuming that the light travels at the same speed. The relationship is that if you take the wavelength and multiply by the frequency of the light, you get the speed of light. So what it means is, because the speed of light is fixed, if I know the wavelength then I also know the frequency. Now, a way to think about this, it doesn't have to be light, it can be any kind of wave. Imagine you've got a water wave that's traveling along like this through the water. It's going this way. And it's traveling with some speed. Okay, so that's fixed. And the water wave has a long wavelength in the sense that the distance between crests of that wave is long. So imagine I've got a post here and I'm listening to the water crash into that post as the wave goes by. Okay? So the time between where I'm, the time it takes for me to clap my hands, that's the frequency, right? So a higher frequency would be like this. And a slower frequency would be like this. Right? Does that make sense? So if the water wave is traveling at the same speed, and I've got a slow frequency like this, that means there's a long distance between the crests. See what I mean? So that means a long wavelength. But if instead I'm seeing this, but I know it's always traveling at the same speed, that means there's a short distance between the crests. So it has a short wavelength. Does that make sense? So it's the same thing with light. If you know how fast it's going and you know the wavelength, then you can turn that around and understand the frequency. Okay, so that's basically what's going on, and for all type of wave phenomena, that's what's happening. It's like that for sound waves, etc. Yeah.
For all forms of light, does like the wavelength for that certain light always remain constant? The length between each crest?
Well, in principle, okay. So imagine empty space. It's like all physics problems. Let's imagine a situation that doesn't ever actually exist. Okay, so we have empty space, nothing's interacting with anything, and I shoot monochromatic light, meaning I shoot light out at some wavelength exactly. It will stay at that wavelength and propagate forever at that wavelength. Okay, but light, in principle, can interact with things and change colors and change frequency and etc. But in the most idealized scenario, what you said is right. If you have light that's shot out at one color, it'll stay at that specific wavelength and keep going unless something acts on it to mess it up. Okay. So the longer wavelength light has smaller frequencies, and shorter wavelength light has higher frequencies. Now there's one final wrinkle that someone mentioned right in the beginning. You mentioned, well, what's light? Well, it's a particle in a wave. And so the thing that we understand now, and I'll come back to this in a bit, but the thing that we understand now is that short wavelength light, that is high frequency light, is made up of high energy photons. And I mentioned this before. So gamma rays have very high energy photons. Radio waves are made of very low energy photons. And the photons of infrared light are somewhere in the middle. And the relationship specifically between the energy of the photons in the light and the wavelength is just this, in that there's a constant divided by, there's some constant, and you divide that by the wavelength. And that gives you the energy of the photon. The shortest way to write it is the frequency of the light times this variable h. This is a constant called Planck's constant. It's a fundamental constant of nature. Planck's constant times the frequency of light is the energy of the photon, of that light. Are there questions about this? So if you know the wavelength of the light, you know the energy of the photons that it's made up with. Yeah?
Yeah, can you just repeat the
What,
word explanation?
Yeah. So if you have a photon and it's making up light that has some frequency, and this variable, by the way, is called nu. It's the Greek letter nu. So if you have some frequency nu of light, like some hertz, you take Planck's constant, which is just a number that has units, and you multiply it by the frequency, and you get an energy. And that is the energy of each photon that makes up that light. Okay? Now, Planck's constant has units of energy divided by frequency. So if you multiply it by a frequency, you will get an energy. That's how it's designed. Now this Planck's constant is very important. Like I said, it's a fundamental constant of nature as far as we understand it. And it's so important that you can type it into Google and Google will tell you what the variable is, what the number is. You know you've made it if you can type it into Google and there's sort of an automatic answer, right? So this is proof here. You don't have to believe me. Just type it into Google and Google will tell you what it is. And so it's this number in these units, meters squared, kilograms per second. The units of energy that we haven't really talked that much about are such that if you multiply this times the frequency, that is a unit of energy. And we will talk about energy later in the course. So I'm not going to spend too much time discussing implications of this right now. I'll come back to it later. I'm going to talk about it later. But I just thought I wanted to give you an introduction to light, just broad brush, and this is what we know about light. All right. So longer wavelength stuff, lower energy photons, shorter wavelength light, higher energy photons. Forgive the fact that I can't spell. All right. So questions about this kind of this qualitative point? All right. So before I go on and kind of back up and talk about the history of this stuff, let's talk a little bit about why things have the wavelengths they do. So what determines the wavelength of light that's emitted by an object? So certain things shine, right? Why do things shine? Like why are some things shining red? Like why does when hot coals get hot, they glow red? And why is it that the sun is glowing sort of yellow? Why do things emit light at different wavelengths? Does anyone know? Yeah.
Is
Yeah.
that where the electrons get excited and the electrons not release simply?
That's one reason why stuff emits light. You're right. So one physical phenomenon for how and why things emit light is that we now know that things are constructed of atoms, and when electrons fall from energy levels in atoms, they will spit out light, and that light will have a specific wavelength, and we'll see that as a color or detect it with a certain wavelength. I'm talking about something actually though that's even simpler than that. Is there anything else that people can think of? Yeah.
Like only certain wavelengths of light are reflected off.
Yeah, that's something else. So that's why things have certain colors. When you shine light on, you shine the same color of light on things in this room. We're all bathed in the same light. Some of us are wearing blue shirts and some of us are wearing yellow shirts or whatever, and that's reflecting. So I'm reflecting blue and her shirt's reflecting yellow. Yeah, that's right. But let's go back to the hot coal analogy. So why do coals glow red? Yeah.
The temperature?
Temperature, right. Right. Is that what you're going to say? Yeah, so temperature is another thing, it turns out, that matters. So this specific type of radiation is called black body radiation. And that's probably the simplest type of radiation that we know about. So the simplest depends only on the temperature in the sense that hotter things glow at shorter wavelengths. And I'll return and talk about the details of black body radiation in the next lecture. But that's just kind of a basic thing to think about, that the hotter something is, the shorter the wavelength light that it will glow in. And the cooler something is, the longer wavelength light it will glow in, right? So, we have temperatures that are cool compared to, say, like a hot coal, right? So 98 degrees or something like that Fahrenheit. And we are, in fact, glowing, okay? Everybody in this room is glowing, right? But we're glowing in light that you can't see. We're glowing in infrared light. That's the heat, okay? So if it were hot enough in this room, you would know it, right? Because your neighbor would be all hot and they'd be radiating on you and that would be really annoying, okay? So we're all glowing, but we're glowing in infrared light that we can't see. Whereas a hot coal is so hot that now it's glowing in light that you can see. And the sun is hot. The surface of the sun is about 5,000 degrees, and so it's glowing at yellow, basically. And so something else you can associate with different types of light is the temperature scale associated with that glowing. Right? So The sun is about 5,000 degrees. So on this chart, okay, it would be, you can see it would be producing light that's, with a frequency associated with something like yellow light. And this is the visible band right in here, okay? So it's probably not that surprising that, we're orbiting around a sun that's spitting out most of its light right around this wavelength range. Our atmosphere also happens to let that light down to the Earth. So it's not that crazy that we've evolved with eyes that detect that light and use it. If you had something that was 10 million degrees, it would be glowing in the X-ray. And there are lots of things in the universe and in our galaxy that are glowing at those kind of temperatures. And that's one reason why we want to launch satellites into space, so we can study those things. Because you can't see the X-rays coming from space most of the time because they just don't penetrate through the atmosphere. So on this chart, you see the very top band there says, yes or no, whether it penetrates the atmosphere or not. And you can see all these short wavelength, high energy things typically don't penetrate the atmosphere. Visible light does, etc. Radio light does. Are there any questions about this kind of general, just this general overview before I keep moving? Okay, so I always think it's kind of fun to back up, and given what we know now, it's interesting to ask the question, how did we get here? How do we know these things? And what was the progression of thought that allowed people to eventually figure this out? It goes back to your question, how do we know what the wavelength of light is? How do you know that? That's a pretty small size. You can't measure that with a ruler, right? So how do we get to this point? So I think it's worthwhile then to back up a little bit. And so we'll start in the boring place where we always start, with the ancient Greek philosophers. Okay, and so this is my spotty historical overview of humanity's understanding of light. This is not complete. Okay, I'm not a historian of science, so forgive me if I miss some subtle thing. But this gives you a general idea of what people were thinking over the course of time. So, let's go back to 450 BC. And what were people thinking about in terms of light? What is light? What is this stuff? Okay. So Plato and Empedocles are examples of people who were trying to figure out how is it that we see, for example, right? And they had this idea that there was some kind of rays that were coming from your eyes. So you open your eyes, and some kind of visual fire shot out of your eyes, okay? And this is fundamental to how we see. Now, of course, this can't be everything, because when it's dark outside, you open your eyes and you can't see. So there has to be something else. And so their idea was, well, that visible fire you have coming from your eyes joins with rays coming from other sources like the sun. And those two things together help you form an image in your eye. So it's like you reach out and get it or something and see. The other thing that they both talked about is whether or not this light that they were sort of intuiting moved, or whether it just existed. So did it travel, or was it just there? And certainly with our everyday experience, it's hard to know whether light is traveling, right? It's just there. Okay, you go outside on a sunny day, it's just bathed in light. So it could just be this stuff that just exists, and it's just always there. Now, Empedocles thought that light was fast, but of finite speed. He thought that it was impractical for the thing to be infinitely fast. But of course, he had no evidence of that. It was just sort of his philosophy. Now, Aristotle said that the light's there, but it does not move. That is, it's sort of instantaneous and there. So it has no motion at all. That's what Aristotle thought. And in fact, this idea held sway with scholars for centuries. It's amazing how many ideas Aristotle pushed through that just dominated schools of thought that were just wrong, just so wrong. It's actually kind of amazing. It's sort of a testament to just how good he was at making arguments, basically. and that his ideas lasted so long, and they were just so wrong, like his ideas on life and just everything were just wrong. But anyway, so he thought light didn't move, and it was there and had no motion. Euclid said that light travels in straight lines. So it travels, and it travels in straight lines. Okay? And in fact, he studied the law of reflection, which is an important law if you want to understand optics. This idea that light comes in and bounces off at equal angles. So this is Euclid, the same great geometer. He was also studying light. Now, he wondered about this idea that Plato and others had talked about before, that if sight came about because a beam of light left your eye, how is it that you see the stars instantaneously as soon as you open your eyes at night? So if somehow you had to open your eyes and there's some beam of something went out, the stars, these really, even he knew they were far away. These stars that are far away, you open your eyes and they go out there and they hit these things. Why does it take so long for you to see them? I mean, sorry, why are you seeing them instantaneously? Why isn't there some delay? If there's some delay time. All right. Now, let's jump forward more than 1,000 years. And in this time period, the greatest scholars on earth were living mostly in Baghdad. Baghdad was a big city of learning at this time. And this guy, Al-Kindi, who was a philosopher living in Baghdad at the time, had made pretty sharp arguments that something's coming into your eye. It's not the other way around. Okay? Now, I want to emphasize again just how long people have been thinking about this idea and how they still didn't really have an answer. And it was sort of a great breakthrough to realize that the fact that stuff's coming in to your eye and not the other way around. So just how mysterious this idea of sight was, that this is sort of where we were. Around the same time, this guy Salih was also studying light in the same city. He discovered the law of refraction. Does anyone know what that is? So the law of refraction is now in modern jargon, we call it Snell's law. And it's basically the idea that light bends when it travels from one material into another. All right? So like you're in a swimming pool and you look down, and sometimes your legs look like they're sort of not right down beneath your body. They're sort of over here, right? That's because the light, when it goes in, is bending into the water, or also when it's reflecting back out. All right? And so if your mind doesn't know how to deal with that, and so you just interpret that as your legs are moved over. Okay? But that's just a phenomenon of light when it travels through two different materials will bend. So this idea, and that's the fancy word for that's refraction, and the idea of that, the fundamental reason, one fundamental thing we do with refraction is you build lenses. Okay? So if you've got lenses on your eyes because you're wearing glasses because your eyes aren't perfect, right? That's because optometricians understand what light does when it enters different kinds of materials, different kinds of plastics. And you can bend the materials and do what you want to do to make sure your light is focusing the right way so your eye can interpret it correctly. So these kinds of ideas, that these sort of philosophers and scientists were working on in 1000 AD, they were working on, in fact, computing shapes of lenses that you would need to do to focus light and to sharpen vision. Of course, lots of advances started happening around the year 1500. But it's still a slow progression and I think an interesting historical question. So Kepler discovered something called the inverse square law and the intensity of light. This idea is going to be important for us in a few lectures. This is the idea that the intensity of light that you see falls off like the distance to that thing squared. So if you're twice as far away from a source of light, the thing will look 4 times dimmer to your eye. And by understanding that inverse square law, that's one thing that allows us to estimate the distances to things. If we think we know how bright they are intrinsically, we can figure out how far away they are. And your brain does this kind of for free automatically, right? If you see someone with a light bulb who's far away, you know that person's far away because the light bulb looks dim. Okay. Galileo concluded that the speed of light is very fast. And I'll talk about this. He actually tried to measure it directly. And he concluded it was too fast for him to measure, that's for sure. Newton did this fundamental thing that I talked about before. He used a pair of prisms to figure out that white light is made up of a combination of all the colors. Now, an idea at the time was, people knew, of course, that when light goes through glass, sometimes it makes a rainbow. Okay? Light goes through a prism, it looks like a rainbow when it comes out. But a lot of people thought that the reason why this happened is because the prism was somehow creating those colors. Right? You put light in and the prism makes the light all these different colors. But what Newton did is he sent light through the prism, broke it up into colors, and then used a mirror to break away only the blue part, for example, of the rainbow, fired that through a prism, and showed that when the blue light went in the prism, it just came out blue. Meaning that the white light that went into the prism was actually made up of all these colors that got spread out. So this is crucial, right? Because this is the very beginning of understanding that light is made up of lots of different colors. And of course, colors is now what we associate with wavelengths. Okay. A lot of people at this time thought that light was a wave. And I won't go into details of why, but you can do experiments, pass light through slits. And if light's traveling in straight lines, it ought to just go straight. But what you find is that light spreads out quite a bit over time as it passes through small holes. And so a lot of people argued that because of that phenomenon, light is actually made up of a wave. But it was debated back and forth. And in fact, Newton said, no. It's not right. Light is not a wave. Light is made up of particles. It's made up like a sea of little BBs. And he said the reason why I know this is true is that light cannot go around corners. All right? If I shine light into a hallway that then bends, it stops casting a shadow in a straight line. It doesn't go around the corner. But if you have a wave coming in on a lake, and the lake has a square dock or something, and a wave comes in along the dock, it will just flip right around the corner of the dock. Right? It's hard to hide from water waves. They'll just go around corners and whatever. Okay, you see what I'm saying? So waves, like in the water, will go around docks and go around corners and things. But Newton said, no, light doesn't do that. Light travels in a straight line. All right? Now, the reason why Newton, turns out, we talked about this, Newton is wrong. And the reason why Newton is wrong about this is that the wavelength of light is so small compared to most of the shadows that we study or that are cast that you can't tell. As long as the wavelength's really small compared to the things that the light is interacting with, then it will basically act like it's going in a straight line. If that makes sense. Okay. Now, the thing I want to talk about, I'll go into a bit more detail on this, is this astronomer named Romer, right around the year 1700, before the year 1700 AD, measured the speed of light. He measured it very precisely. And you might ask yourself, how is this possible? And the way he did it is he studied the moons of Jupiter, one particular moon of Jupiter. So I will skip over this stuff because this is more of the modern understanding of light. There are a few key figures who played important roles in our understanding of light in a modern sense. Thomas Young basically did a definitive experiment to prove that it really did behave like a wave. And I'll come back to this in a bit, but this was by showing that it produces what's called an interference pattern. James Maxwell wrote down the overarching theory of electromagnetic radiation via the Maxwell equations, and basically showed that one theory could describe all radiation, all phenomenon of electricity and magnetism together in one theory, and basically said light is definitely an electromagnetic wave. Now, there was a weird problem. So everything was looking rosy. Light is clearly a wave. We've even got a theory for it. Newton was wrong. His arguments were wrong because the wavelengths are so small, etc. And then all of a sudden, there's this one weird thing that was discovered that's known as the photoelectric effect. The photoelectric effect is that when you shine light on a metal plate, it's very detailed, but there's a really interesting payoff. The energy that's released off of that plate depends only on the wavelength of the light that you shine on it, and not the intensity of the light that you shine on it. Okay? So you might think that if you have a metal, what's going on is you have a metal plate, you shine light on it, electrons start popping off. And you measure how fast those electrons are going when they pop off. Now you might think if you have light and you have like one light bulb, you measure electrons start popping off, you're heating it up, electrons are popping off. You measure how fast the electrons are going. Then you get 30 light bulbs that are identical and shine them on the same plate. Now you might think, oh look, there's so much more light shining on it now. Now these electrons are really going to be popping off. It turns out that more of them pop off, but they're still all going at the same speed. They're not any more energetic than they were before. This is totally different than you would have guessed if all that was going on was wave-like motion. The person who solved this conundrum is a guy named Albert Einstein. So Albert Einstein said, oh, well, I know how to solve it. If light's made up of particles, and if those particles have energies that only depend on their wavelength, then I can fix this. Because what was found is that if you then take a different type of light bulb that produces light, say, that's blue rather than red, then the energy of the electrons goes up. Or if you take a light bulb that shines in longer wavelength light, like infrared light, the electrons that pop off are moving very slowly. So what tended to matter was only the wavelength of the light that was shining on it, and not how much of light that was shining on it. And Einstein said, look, the way to solve this is you make light made up of particles. And today we call those particles photons. This was a crazy, crazy, crazy idea, okay? Because how could something be a particle and a wave at the same time? I think physicists today are still kind of coming to grips with that, how to think about it. Okay, we have a very well-established theory called quantum mechanics that describes the phenomenon very well, but it's a very weird kind of phenomenon that qualitatively is odd, and I will talk more about that in later lectures. But the bottom line is that because of this progression of ideas, today it's understood that light behaves both like a wave and a particle. Specifically, it delivers energy like a particle. So it hits like a particle, but it travels like a wave. So when it travels through space and interacts with things and goes through slits, it acts like a wave. But when it hits and delivers its energy, it delivers its energy in punches, in photons. Are there questions about this qualitative stuff? Okay. So, there's something else you can type into Google. You can type anything into Google. But here's another thing you can type into Google. Speed of light. Type speed of light. It tells you the speed of light. How does Google know the speed of light? How do we know the speed of light? This is a big, fast number, right? How do you set up an experiment to measure the speed of something that's going that fast? Well, ancient people have been tried to do it for a while, and as I mentioned, there's this astronomer named Romer who ended up doing it reasonably successfully. And the way he did it is he used something that was really far away. So if something has to travel a long distance, you might get a chance to measure time differences, even if it's traveling really fast. So the history of this, or a good place to start in the history of people trying to do this, is with Galileo. Okay? Galileo, turns out, wanted to measure the speed of light. He was interested in this. And so he had an idea for how he's going to do this. And I think this is a great example of, it's worth a try. Okay? This is what you do in science. You're like, well, I could try this. Most of the time it doesn't work, but every now and then it does. So he tries this. He says, look, He's going to take his assistant out into a field that's big. Let's pretend like it's like a mile long. All right? And he's going to get a lamp, and his friend's going to have a lamp. And they're both going to be covered up. And then he says, all right, I'm going to uncover my lamp. When you see my lamp, when the light from my lamp shines and you see it, you uncover your lamp. And I'm going to measure it. I'm going to start my watch. I'm going to start measuring as soon as I uncover my lamp. And then when I see yours, I'm going to stop it. And so then I'll know how long it took for it to get to your, for you to see mine and then for me to see you. Does that make sense? And so it's, the distance between their lamps is a mile. All right. So because speed is just distance over time, he knows the distance. And so if he measures the time, he's done. He can measure that speed. So this is what they do. They cover up their lamps. Okay? Galileo opens up his lamp. The light shines off to his friend. And he starts timing. Then his friend sees it, uncovers the lamp, and then goes back. All right. You think this is going to work? Probably not going to work. Moreover, he's using a pendulum clock. So probably not going to work that well. And what he found is he couldn't measure any difference. I mean, he's like, and then as soon as he took his off, he'd just see it. So what he concluded, though, was that light was 10 times faster than sound. Because if you do the same experiment with yelling to each other, you can actually measure a sound speed. Okay? So he's like, it's at least 10 times faster than sound. That was his conclusion. But it's an interesting conclusion. It's it's worth the measurement. So let's just get a sense of this, right? So the real speed of light is 186,000 miles in a second. All right? So time it takes for light to travel a mile is like 5 millionths of a second. So you're not going to measure that with a pendulum. So it's no wonder he couldn't do it. What you need is something that's farther away, some kind of phenomenon that's farther away that you can start to kind of measure. So something that it's so far away that even light, it takes a little while to get there and come back. And the first person to really do this successfully was Ole Romer. And he was studying Io, which is this inner moon of Jupiter. And this was 1676. Okay, it's 100 years before 1776, right? So it's a long time ago. Measure the speed of light. So the deal is, the thing that matters the most, this is a movie of Io going around Jupiter. Okay? And what you see in this movie is, Jupiter's lit up by the sun, and so is Io. And when Io goes behind Jupiter, compared to the sun, it gets dark. And it comes back out again. All right? So it gets eclipsed and then comes back out. Okay? And it takes Io about 42 hours to go all the way around Jupiter. So it circles Jupiter once every 42 hours. So it's just orbiting around like this. And so you can watch this, right? So this is something you can go out with a telescope like they had then. And you can watch this thing. You can track Io going around Jupiter and measure how long it takes. And so it goes away, then it comes back. It goes away, then it comes back, right? And that amount of time that it's dark just depends on how long it's taking this thing to orbit. So he was timing how long it took for the thing to go behind Jupiter and then come back. And he noticed this weird thing. Okay? He noticed that it took longer to reappear depending on where the Earth was in its orbit. So certain times a year, it would be gone for a smaller amount of time than it was in other times of the year. And he thought to himself, why is this? Because there's nothing, the Earth isn't doing anything to Io, so why would it matter where we are? So what he said is that the Earth's distance to Jupiter changed as the Earth is going around as the Earth is going around the Sun. So the Earth would be a little bit closer to Jupiter when Io poked out sometimes, and sometimes the Earth would be a little bit farther away from Jupiter when Io poked out. So light would have shorter and longer distances to travel depending on what direction we were moving while it was behind Jupiter. Okay, so the basic idea is, so here's the Sun, here is the Earth going around, all right? And so that figure up there at the top, that's Jupiter casting a shadow, okay? And so when Io goes behind Jupiter, it gets dark. And then it takes it a little while to go from C to D, up there. While it's going from C to D, the Earth is moving this way, right? So now when it pokes back out, the Earth is closer than it was before, so it doesn't take light as long to get to us as it did. Conversely, when the Earth is over here going around the Sun, remember it only takes 42 hours for this thing to circle around. So, you know, you wait 6 months and now you're over here. Now you're traveling this direction. So now you see it go behind. Then you move farther away and it pokes out, but now the light from Io has farther to bounce back to us. So it takes a little bit longer. So that there's a little bit of delay for it to light up again. Yeah?
Jupiter isn't stationary either, though.
Yeah, we're all moving. We're all moving, but there's still the difference, you know, the distance between us and Jupiter changes over the course of a year, and depending on which year it is, the distances are different. But, you know, this is over the course of a single year, this isn't a bad, it's not a bad approximation that our distances aren't that far, because it takes Jupiter a lot longer to go around than it does us, because it's farther away. But you're right, it's a little bit more complicated than that, but that's the basic idea. Right, so let me just show you one more time. This is the Earth going around. Here's the Sun. This is a totally not to scale, doesn't make any sense diagram, but basically here's Jupiter and here's the orbit of Io around Jupiter, and this blue thing is supposed to be the shadow cast by Jupiter. Right. So, you know, when the Earth is moving this way away from Jupiter, path B for light is longer than path A. All right. Conversely, when we're going this way, path D here is shorter than path C. So the time delay, the time it takes light to travel once Io is revealed is different depending on where we are. That was his argument. It's a pretty sophisticated argument too, right? I mean, it's amazing that he was able to do this and believe his own measurements of Io and all that kind of stuff. So you can see from this, if you know how far away the Earth is from the Sun, and therefore you know basically how far the Earth is traveling during these periods of time, you can then use that distance to get a speed for light. And because that distance is obviously much, much, much farther than a mile, you have hope of measuring it. So he made a prediction. So in September of 1676, he made an announcement. So he just started going, he was pretty confident because he predicted it once himself and he's sort of convinced that he was right. So then he made a big deal out of it. He said, look, I can make a prediction here, all right? So he told members of the Paris Academy of Sciences that the next expected eclipse, so they knew there was going to be another eclipse of this moon, he said it's going to occur exactly 10 minutes later than computed on the basis of previous eclipses. And he just kept repeating it and kept yelling about it and talking about it. He wouldn't shut up about it. So finally they were like, fine, let's look at this and see this crazy guy thinks he's going to change this. And this is what they found, right? And he was able to say that the speed of light was such that it would take 22 minutes to travel the diameter of the annual orbit of the Earth. Okay? So he said, based on all these calculations and the measurements that he's got, it should take 20 minutes to travel from here to here. The real answer is 16, but pretty close. So, not a bad measurement. Basically, he got the speed of light more or less right, certainly within to about 50%, in 1676. That's pretty impressive. Is there any questions about that? Okay. So, through a series of sort of very slow, progressive arguments like this, each one of them very clever and careful, eventually we built up this understanding of what light's doing. We have a sense of how fast it's going, how it behaves, and all this kind of stuff. And so the modern view of light is a very kind of weird thing, okay? In the sense that it's like nothing we're familiar with in the macroscopic world in our day-to-day experience. So it's not correct to think of light like a little stream of pebbles that's just sort of propagating out of flashlights or something. It doesn't behave that way at all. But it also doesn't behave like a pressure wave or a sound wave either. It's somehow fundamentally different than both of those kind of things. It doesn't act like a particle or a wave. It travels through space like a wave, but it hits things and it gives up its energy like it's made of particles. So when I say that it travels through space like a wave, what am I talking about? So waves and particles are very different things. And wave phenomena in mechanics is something that was understood for, going on the time of Newton. And so one of the things that we understand about waves, and I mentioned this before, is that they do something called refract. That is, their trajectory bends when they enter a medium that's different than the one they're traveling in. So if you have a wave that's traveling through air and it enters water, it will bend. And a qualitative way to think about that is if you have waves, if you think about waves coming in along planes, sort of imagine sort of sheets of things propagating along, and you come into a different surface, say like water. So light travels more slowly in water than it does in air. So what happens is the edge of this wave crest will start to go slower than the stuff that's still out of the water, and effectively what that will do is it will sort of bend it. Like this part of the wave will sort of break, and this one will keep going, and it will create a bending. And then the light will travel through the water in some way, and then if it comes out the other side, it'll bend back the other way. Okay? This phenomenon of bending when you travel through different media is called refraction. All waves do this. All waves refract. And light refracts. So I mentioned this before. In the history of the studying light, it's very well understood that light refracts. That's why we can build lenses. Okay? Light bends when it travels through different kinds of materials. It's also basically the reason why prisms work. Okay? Because different color light refracts in a slightly different way than others. So the blue light's bent more than the red light, or I can't remember. The other things that waves do is they interfere with each other. All right, so if you have two waves that are traveling along, imagine you have two water waves, and there's two high crests that are coming together, and they merge. Then you make a really high crest. It's double the height of the two coming together. Or if two waves come together and you have a high point of the wave and the low point of the wave and those two cross, then you get nothing. Okay? So that's called interference. So you see that here, just two pebbles have hit a pond, and where the two water waves kind of start interacting, you get phenomenon that's not like adding two things together. Sometimes they can actually subtract. Right? So you can create destructive and constructive interference. Constructive interference is you sort of amplify the wave, and destructive interference is when you break it down. Are there questions about that? Yeah?
There was destructive interference and the other one was
Constructive interference. So destructive interference is if you have two waves that line up in such a way that a peak of one wave lines up with the trough of another, the low point of one interacts with the high point of another, you basically, that creates a zero. One's like positive and one's negative, that creates a zero. So you can work out sound, like for example, complicated, noise canceling headphones that you wear. That's kind of what those are doing, right? They're creating interference in the sound waves that zeroes them out. So even though you have a really loud sound coming in, you can create use the wave-like phenomena of the sound to basically deaden it, to cancel it out in principle. For related reasons, actually, yeah. Or you can create constructive interference. So if you have light that's interfering with itself, it can create higher points. And you may have seen this in a wave. Is anyone, probably people around here don't do this, but I grew up in the Midwest, and you used to do this crazy thing. You used to go to water parks where they have wave machines, so you could experience what it would be like and be in like a real ocean with waves. And so, if you're in one of these pools that's creating waves, every now and then they get synced up, and you have two big waves that come together in the pool, and you can just go way up in the, just crazy high up, And so you really get a sense of what constructive interference is. It's almost like when you're on a trampoline and you can time the bounce, so you do the double thing and then you go way up high. It's that kind of constructive, it's sort of like constructive interference, okay? It's sort of a wave-like phenomenon. And light does this as well, okay? Light does it, sound does it, all types of waves do it. The final thing that sound waves do, or another thing that sound waves do that normal stuff doesn't do, is exhibit something called the Doppler effect. And the Doppler effect is basically the same phenomena where the pitch of something changes depending on whether it's traveling towards you or away from you. So this is in sound, right? So if a car is coming towards you, if it would just sound like this if it was near you, nah, okay? But if it's coming towards you, it's like, nah, and then it goes away, that, that's the Doppler effect, okay? So it's high pitch to low pitch. What's going on is, if you're traveling towards a sound, the peaks of the wave, the sound wave, they pile up close together, and it sounds like a higher frequency because those sounds are hitting your eardrums more frequently. So it's a higher frequency. The other way around, if you're standing on the far side of the car and it's going away from you, those peaks are stretching out, and that's a drop in pitch. Okay? Light does the same thing. Okay, if you have a source that's traveling away from you at a high speed, the color of that light will be shifted to longer wavelengths. It'll look red. That's called redshift. And if the thing is traveling towards you, the color of the thing will look blue. That'll be blue. It'll look bluer. That is, the wavelengths will be shorter, and that's called blue shift. So light exhibits this Doppler shift type phenomenon. That waves are basically stretched out or compressed relative to the listener, depending on whether the source is going towards you or away from you. And again, this is a wave-like phenomenon that only makes sense when you think about waves. And light does this, okay? Light interferes with itself, creates constructive interference patterns, destructive interference patterns. It exhibits the Doppler shift, something we call redshift and blue shift. And it also bends when it goes through different types of material, so it refracts. All right. So light refracts, okay? You've seen this. It creates interference, and it creates blue shift and red shift. Now, the weird thing is that it exhibits this other thing called the photoelectric effect, which I talked about before. And this is a big deal because no one understood how to make sense of this experiment, because this would not be, the results of this experiment would not have held for electromagnetic radiation that was purely a wave. So basically what happens is this. You have a metal sheet. I know it sounds very boring, but you do something very, very simple and see if you can understand what happens. And if something weird happens, that suggests that there's a fundamental law that you're missing. Okay? So it sounds like a very dry experiment, but that's the point. You want to break it down to its simplest terms. So what's the boringest, most dry thing you can do? You take a plate, metal, you shine light on it. When light hits that plate, electrons start flying off. You've delivered energy to the electrons in there, and the electrons can't be held by their metal anymore, and they start popping off. What you find is that the speed with which those electrons pop off depends only on the wavelength of the light you shine on it. And in fact, if you make the light that's shining on it long enough wavelength, nothing happens. No electrons fly off. Even if you shine 1,000 light bulbs on the plate, if it's a long wavelength light, no electrons pop off. But then you just take one light bulb, shine it on there, and just make its wavelength a little shorter, say red light. Then electrons start popping off with some energy. Then you make it blue light, and then electrons start popping off with even higher energy. This is not going to happen if the only thing that's going on is you have waves hitting this, electromagnetic waves hitting this metal. And so this was a mystery, okay? And in 1905, there was a young guy named Albert Einstein who had just gotten his Ph.D. And he had also that same year published a theory was working on a theory called the special theory of relativity, which he knew was right. He's like, I know this is definitely right. This is going to be awesome when people read this, okay? This one, he was like, boy, I don't know what to make of this, but I have a crazy idea. I'm really nervous about publishing this, but I'll just put it out there anyway. What if the light only deposits its energy in quanta? What if it only deposits its energy in little bits, and those little bits have energies that depend only on the wavelength of the light? It's not continuous energy deposition, it's quantized energy deposition. So it can only deposit its energy in bits. Not a continuous bit, not a continuous stream of energy, but only in pieces. Like it was somehow made of particles. Even though we know it's not made of particles because it refracts and does all this stuff and does Doppler effect and all this kind of thing. But what if? And he found that if he did that and he made this really simple assumption that the energy of the photon was related directly with the frequency of the light, everything works. And it's very simple. It turns out that Einstein was eventually awarded the Nobel Prize for this. He wasn't awarded the Nobel Prize for E equals mc squared or anything like that. He was awarded a Nobel Prize for this. These photons, these particles today are called photons. And I've talked about that. And the relationship is this equation. E equals h nu, which is the same as hc over lambda, where lambda is the wavelength, and nu is the frequency. This is now how we are forced to. Nature forces us to interpret light this way. We call this a particle-wave duality, all right? And it's a strange thing, and it's intimately connected to the modern theory of quantum mechanics, which was developed by lots and lots of physicists over the 20th century. According to quantum physics, in fact, everything, not just light, has a particle-wave duality. And this particle-wave duality is intimately linked to the fabric of the universe and the fundamental laws of physics. And it was discovered through studying light. Let me end by describing to you how strange this is. And you know, probably most of you have heard this before. In fact, the first answer I got when I asked what was light, is someone said it's a particle in a wave. So you've probably heard it. How many people have heard this before? I just wonder, right? Many of you have heard it before. Not everybody, but many of you have. And those of you who've heard it before, you hear something enough, it doesn't sound weird anymore. Okay? The Earth is moving. We go around the sun. Fine, that doesn't seem weird at all. Okay? But let me just give you an example of how this is weird. All right? So this is what light interference is. Okay? You take a light, a source of light, and you make a small slit. You have a black, a wall with a very small slit in it, and you shine light through that slit. The light will spread out on the wall and just make like a blank, a filled pattern on the wall. It will just cast like a spread out shadow on the wall. Then you put another slit next to it, and you shine light through that double slit. Light will create an interference pattern on the wall. What that means is there'll be a band of dark, a band of light, a band of dark, a band of light. And the reason why it does that is the two wave sources coming from those two slits will now interfere with each other as they propagate. And the dark spots are where peaks and crests line up to create zero, and the bright spots are where the two peaks line up. Okay, so if you have 2 points of light, they're both propagating waves. depending on where they hit on the wall, they've traveled different distances. So their peaks line up in different places. All right? And so you get, and that's what this diagram here in the upper right represents. You have light going through two points, and you create an interference pattern on the wall of bright and dark spots. All right? That's classical physics. You can do this experiment for yourself. I know you're all dying to do that, and you're welcome to do that as soon as we're done here today. Now, let's do something weird or hard to do, and let's see what happens. I'm firing light out of my gun here, right? But let's say I can tune it in such a way that I only spit out one photon at a time. Okay? And when I spit out one photon at a time, the light comes out, boop. And then I wait for a while, and it hits the wall and goes and creates a white little dot, little bright dot on the wall. Now I spit out another photon, just one. It goes through the slits and hits the wall and makes another spot on the wall. Okay? Now I've only shot 2 photons. I wait a while. Then I shoot another one. I keep doing this. You guys all leave because you're getting bored. You come back in a few hours and look at the wall. What's happened is a lot more photons have hit in the bright spots and none have hit in the dark spots. So what you end up with on the wall is a band of bright points and dark points that were all created by individual photons hitting the wall. So people have done experiments like this, actually using electrons. It's easier to do. And you see this effect directly, as if the photons are somehow interfering with themselves as they go through the slits. This would not happen with BBs. You know, if I had a BB gun and I was just shooting BBs through this thing, I'd just get a random assortment of BBs on the wall. There'd be no pattern. But if you do this with light, with photons, you get this sort of self-interference of photons. And so it's this kind of thing that is at the heart of this particle wave duality. That even individual photons worth of light travel and interfere with themselves like waves. And only when they hit the wall do they hit with specific deliveries of energy. And it turns out that that phenomenon of light, that it's made up of specific wavelengths of photons that interact in very specific ways, is fundamental to our ability to understand what things are made of that are millions of light years away. And I'll talk about that next time. All right, thanks.